Let's take a look at one more application of the cross product. We're going to look at how to find the distance from a point to a line in three-dimensional space. In order to be able to measure the distance from a point to a line, we need to take notice of a couple of things. When we measure distance in space, we're going to be measuring along perpendiculars. The shortest path from a point to a line is going to be a perpendicular path. And so we can use vectors to make these distances computable. Here we have a formula that tells us that the distance from some point Q to some line r equals r naught plus t times a vector v is going to be given by the cross product of that vector v and the vector pq divided by the magnitude of the vector v. So p here is any point on the given line and v is any vector parallel to the line. So let's look at why this is the case. So if we have 3 dimensions, I'm going to draw my 3-dimensional coordinate axes here, and we have our line R, some line in space. So this is the line R, and we have some point Q that's not on R. And what we want to do is drop a segment in 3D that's perpendicular to R from Q. And now we want to find, we're going to call that that length of that segment D. That's the distance, and we're trying to find that. So all we have to do is pick some arbitrary point anywhere on this line. We'll call it P. And we can connect P to Q with the vector PQ so that the length of that segment is the magnitude of PQ. And then we also know that along here, we have some vector V, which is equivalent to the vector V that is our line vector. All right, so given that picture, now we have the angle in here, we'll call it theta. And we know from trigonometry that the sine of theta is going to be d divided by the magnitude of PQ, which tells us that d is equal to the magnitude of PQ times the sine of theta. All right, that's not our formula yet, but let's think about what we know. We know that the cross product of our vector v and PQ, the magnitude of that cross product, is equal to the magnitude of v times the magnitude of PQ times the sine of theta. Well, this is d. So now we have that the magnitude of v, the magnitude of the cross product of v and PQ is the magnitude of v times this quantity d, and then we can solve that for d to get the formula above. So if we have the equation of a line given in vector form so that we have a vector that we know is perpendicular to the line, we can use that and we can choose any point that we want that's on our line, and that will help us find the distance from the point to the line. Let's put the formula into action with an example. So here we have the point 2, 1, -1, and the line given in vector form 1 plus t, -2 plus 2t, and 3 minus t. So first, let's check that the point is not on the line. If it were, then we'd have some value of t where 2 is 1 plus t, and 1 is -2 plus 2t, and then also -1 is 3 minus t. So if we solve these first two for t, adding these up, we get 3 equals -1 plus 3t. So that's 2 equals 3t, and t equals 2/3. But if we plug t equals 2/3 into here, into the last equation, -1 equals 3 minus 2/3 is false. So that tells us the point is not on the line, which is good. If it were, then the distance would be 0 and we'd be done. We could also use our formula, our distance formula, and we would get a cross product of 0, and that would indicate to us that the point is on the line. So if the cross product ends up being 0, you know also that the point is on the line. Anyway, neither here nor there. Let's move on. So here we need a point that's going to be on the line. So we're going to choose our point P. Let's let T be 0. Then we know the point P equals 1 plus 0 is 1. Negative 2 plus 0 is negative 2. And 3 minus 0 is 3. So there's a point that's on our line. Our vector v comes from the coefficients of t. So we have our vector v is going to be the vector. Whoops, I wrote p as a vector, and I want it to be a point. So v is going to be the vector coming from the coefficients of t in our linear equation. So v is the vector 1 to negative 1. Okay, so now we know that our distance is going to be the magnitude of the cross product of the vector, v cross pq divided by the magnitude of v. So we have a few things to find. First of all, let's find the vector pq. PQ, it starts at P and ends at Q, so we're going to take all the coordinates of Q. This is our point Q up here. I never labeled it as Q. Or the point Q is the one that's given in the statement of the problem. So the vector PQ is going to be 2 minus 1, 1 minus negative 2, and negative 1 minus 3. 1 minus, yes, that's right. Okay, and so let's do V cross PQ. So we're going to take our determinant of this matrix, 1, 2, negative 1, 1, 3, negative 4. And we're going to get, let's see, negative 8 minus negative 3 times I minus negative 4 minus negative 1 times j plus 3 minus 2 times k, which is going to be negative 5i plus 3j plus k, so that the magnitude of v cross pq is the square root of 25 plus 9 plus 1. So that's the square root of 35. And the magnitude of v is the square root of 1 plus 4 plus 1, which is the square root of 6. And so we are going to get that our distance is going to be the square root of 35 divided by the square root of 6, which you can just write as the square root of 35 sixths. So final answer, the distance is the square root of 35 over 6. So a lot of moving parts in these, so let's do one more example. So now we have the point 5, 6, 1, and the line x equals 1 plus 3t, y equals 3 minus 4t, and z equals t plus 1. So again, let's go ahead and find a point P on our line. So we'll let P be when t is equal to 0. So P is going to be the point 1 plus 0, which is not 0, it's 1, 3 minus 0, and 0 plus 1. So P is the point 1, 3, 1, which makes the vector PQ is going to be the vector 5 minus 1, 6 minus 3, 1 minus 1, which makes the magnitude of PQ the square root of 16 plus 9, which is 5. Our vector V is going to be the vector given by the coordinates of t. So we're going to get that V is the vector 3, negative 4, 1. And that makes the magnitude of V the square root of 9 plus 16 plus 1, which is the square root of 26. Last thing to do is the cross product. Well, two more things. We have to do the cross product of V and PQ and then find its magnitude. So that is going to be the vector we get. Let me remove the magnitude symbols here, because first I'm finding the vector. I erased too many things there. V cross PQ is the vector that we get when we take the determinant of this matrix So that is going to give us, let's see, negative 4 minus 3 times I minus 0 minus 4 times j plus 9 minus negative 16 times k. So our cross product is the vector, hold on, going back in time to right here. That first coefficient is 0 minus 3. Negative 4 times 0 is definitely not 4. All right, so we get negative 3, and then we get positive 4, and we get 25. So the magnitude of V cross PQ is going to be the square root of 9 plus 16 plus, yikes, 25 squared, which is, I think it's 625, but I'm also going to just check my math because my brain is not 100% certain that's true. Yeah, that, right? 12. Can't multiply this more. Yeah, 625. Okay. Whoa, 625. So we get that that is the square root of 650. I'm sure that simplifies, but now we know that our distance is the magnitude of the cross product divided by the magnitude of the line vector, and so we get the square root of 625. I don't know why I found the magnitude of PQ. It was not at all helpful. Divided by the square root of 26, and this is not 625, it's 650. Which is, of course, let's see, that's 25 times 26 over the square root of 26. The square roots of 26 cancel out, and we see that our distance is 5. All right, as per my usual, we will summarize what we've learned. We know that even in 3D, the shortest distance between a point and a line is going to be the perpendicular. And so we can use cross products to find that distance. The distance is going to be the magnitude of the cross product of V times PQ divided by the magnitude of V, where V is a vector in the direction of the line, and P is any point that lives on the line, and Q is the point whose distance we're trying to find.